itself. So you can conclude that the scalar multiplication is also satisfied. Okay, so these are the two properties that you need to check for you to verify if the set given to you is a subspace of M22 or not. Okay, so these are the two properties, and these properties are listed down in theorem 1. Okay, the results of example 2 can be generalized. That is, for any positive integer n, the set of symmetric matrices of order n is a subspace of the vector space M and n with the standard operations. Okay, so this is the same thing that I've explained here just now, going back to the definition of square matrix. So for 2 by 2 matrix, we know that it is always going to be a subspace because of these operations here. Okay, and a 3 by 3 symmetric matrix is going to have the same subspace property. A 4 by 4 is going to have the same subspace property, provided that the matrix given to you is a symmetric matrix. Right? And symmetric matrix here means that the matrix is equal to its own transpose. Alright, so this can be generalized for n until n. So all of these are going to satisfy the subspace property. Alright, so there's one more example here, the set of singular matrices. Okay, so let me just number this page here. This is the page number 1. Let's go through this example here, example 3. So the set of singular matrices. Alright, so now the definition of singular matrices, what is it? So the definition of singular matrices says that a singular matrix is not invertible. Okay, and then in other words, the determinant is equals to 0, and then the inverse does not exist. Alright, so these are the 3 definitions for a singular matrices. Okay, so if you see not invertible and inverse that does not exist, it implies the same thing. Not invertible means you cannot inverse the matrix. So if you cannot inverse the matrix, it implies that the inverse does not exist. Okay, so these two statements here, they mean the same thing, right? Okay, so let's have a look at the example. The set of singular matrices is not a subspace of M and N. Okay, so for example, let W be the set of singular matrices of order 2. So now you have W is a set of singular matrices of order 2. The question, order 2, what does it mean by order 2? Order 2 here means that you have a 2 by 2 matrix, right? So the question says, show that W is not a subspace of M22 with the standard operation. Okay, so what does it mean by standard operation? Standard operation here actually goes back to theorem 1. Theorem 1. So you have to check the addition part and also the scalar multiplication part. Okay. Okay, so this is the solution is given here. By theorem 1, we show that W is not closed under addition. To see this, let A and B, okay, so you're given these examples here. You have this matrix A equals to 1, 0, 0, 0. And also you have matrix B given by, you have 0, 0, 0, 1. Okay, so remember the choice of the examples that you want to use to perform the addition and also the scalar multiplication must be from the set given to you. Alright, so now you have W is the set of singular matrices. Is this a singular matrix? Yes, it is, because the determinant is equal to 0. 0 minus 0, you get a 0. Okay, is B a singular matrix? It is, because 1 times 0 is 0, minus 0, you get a 0. So these two matrices are singular matrices of order 2, because you have two, this is a 2 by 2 matrix. Okay, so, okay, all right. So now we're going to check the first one. The first one is addition. So you have A plus B. So what will you get from here? So 1 plus 0 is 1. Okay, 0 plus 0 is 0. 0 plus 0 is again 0. 0 plus 1 is 1. Okay, so now let's check. Is this A plus B inside W? Okay, because if A plus B, the addition of A plus B is inside W, then W is a subspace. Okay, but if it's not, then W is not going to be a subspace. Subspace of what? Okay, so the vector space here is given by M and N. Okay, so we want to check if this W is inside this M and N or not. Alright, so now, so based on this one here, is this going back to this set W here, set of singular matrices? So let's check the determinant. So what's the determinant here? Determinant is going to be 1 times 1 is 1, minus 0 is equals to 1. Uh-oh, there's a problem here because W is a set of singular matrices. Okay, singular matrices means determinant equals to 0. Like how we have determinant equals to 0 here, determinant equals to 0 here. Unfortunately, when you do the addition, you get this matrix here. The determinant is not equals to 0. Okay, so for that reason, A plus B is not inside W. So since it is not inside W, this one is not satisfied. Okay, so how about the scalar multiplication? Let's try scalar multiplication on one of these matrices here. So let's say CA is equals to, now you're going to have C0, 0, C. Okay, is this a singular matrix? This is a singular matrix. Let's check the determinant. The determinant here is equals to C times C is C squared minus 0, which is equals to C squared. Okay, so this can be a singular matrix if provided that your C is equals to 0. Okay, because your C is equals to 0, you're going to have what? 0 times 0 is 0, minus 0, then only you're going to get a 0. If this C is not equals to 0, then C scalar multiplication with A is also not inside W, right? Because remember, for a particular matrix to be inside W, the determinant have to be equals to 0. Okay, so you can see both properties of addition and scalar multiplication are not satisfied. Alright, so the conclusion here is that it's non-singular. So W is not closed under addition, and by theorem 1, W is not a subspace of M22. Alright? So this one here is supposed to be M22. Okay. So let's have a look at one more example. This is a subset of R2. So subset of R2, I would like to emphasize again, it is going to be given like in terms of 2 coordinates. Okay, you can have something like A, B. Only 2 elements because this is 2. Alright, so the question here wants you to show that R2 that is not a subspace. Okay, so you are given this W, so you want to check, is W a subspace of this R2 or not? So let me grab another piece of paper. This is page number 2. I can scan all these pages here and upload on Goals if you want to have a copy of it. Okay, I'm going to do that at the end of the recording. Alright, so let's have a look at this example 4. So this is going to be page number 3. Alright, so example 4. In example 4, you are given R2, okay? And the question wants you to check is W is a subspace of R2 or not. Okay, and you know, how are you supposed to check? You're going to have to use theorem 1. And in theorem 1, there are 2 things for you to check, which is the addition and also the scalar multiplication, alright? So let's first of all have a look at the definition of W. W is given by, so you have x1, x2, where x1 is greater than equals to 0. What does this imply? It implies that the first coordinate is always positive, alright? And you are given x2 greater than equals to 0. So this one here implies that this have to be a positive number. This one also have to be a positive number. All right, with standard operations. Okay, so first of all, let's check. What are we supposed to check? Okay, we are supposed to check the addition and also the scalar multiplication. All right. So let's check the addition part. Okay, for the addition, you're gonna have to extract two examples from the particular set given to you. So in this example, you can take A, B. Remember, A and B both have to be positive numbers because this W is defined in such a way that the first coordinate and the second coordinate are positive numbers. All right. So if you take A, B, and then you also take, let's say, C, D. Okay, let's add these two. Okay, let's say this one is going to be W1 equals 2 and this one is W2 equals 2. Okay, so I want to test for W1 plus W2. Okay, so what is it? W1 plus W2. First coordinate plus, wait, this is the first coordinate here. So you're going to have A plus C and then B plus D. Okay, and then what? Now you have to check if this one here is inside W or not. Okay, so A is a positive number, C is a positive number. You add two positive number. Are you going to still get a positive number? Yes, you are. So this part is satisfied. B is a positive number, D is a positive number, B plus D. You are adding two positive numbers. It's going to still give you another positive number. So this part is satisfied as well. So there's nothing wrong with the addition part. Okay, so now this one is satisfied, all good. And now we need to check the second part here, which is the scalar multiplication part. Okay, remember for scalar multiplication part, the scalar that you choose can be anything because in this definition here, this definition is just restricting the values of x1 and x2, but not the scalar value. Okay, the scalar value can be anything. It can be a fraction, it can be a negative number, it can be a positive number, it can be anything. Okay, so let's try for the scalar multiplication. Let's say I choose scalar 1. Okay, multiply with a vector that I take from this W here. Let's say I'm taking vector 2 and 3 because 2 is a positive number, 3 is also a positive number. So 2, 3. What would you get? You will get 2, 3. Is this still inside W? Yes, it is. No problem in that. Okay. So for example, I want to take half. This is the scalar half. Multiply with 3, 4. 3 is a positive number, W is a positive number, it is in this W here. So if you multiply these two here, you're going to get what? You're going to get 3 over 2 and 4 over 2 is equals to 2. Is this inside W? Yes, it is inside W, okay? Why? Because W says that first coordinate positive, second coordinate positive. First coordinate is positive, second coordinate is also positive. No problem in here. So the problem now arises from the choice of your scalar multiple. Let's say if I choose negative 1 and I choose my usual vector here, 2, 3. What would I get now? I'm going to get negative 2 and also negative 3. Okay, so there is a problem here because W is defined in such a way that first and the second coordinate are both positive. But then if you multiply with this negative scalar here, you get negative 2, negative 3. Are these two allowed to be inside W? I don't think so. Okay, so this one is not inside W. So you see, it goes back to the choice of scalar multiple that you are working with for you to check if this scalar multiplication is satisfied or not. Okay, so in this case, you can say that this part is all good, but not this one here. So from here, we can make a conclusion that, let's see what is the conclusion made here. So the conclusion made here is that W is not a subspace of R2. So W is not a subspace of R2. Okay. So next theorem tells us that the intersection of two spaces is also a subspace. Okay. For example, I'm going to just sketch this one here. This is going back to theorem 2. So theorem 2 says that if you have this vector space here and inside this vector space you have, okay, so vector space here is denoted by U. Alright, so I'm going to denote this vector space as U, U, which is a vector space. And then if V and W are both subspace of vector space U, let's say you have this V, okay, V which is a subspace. How do you know V is a subspace? How do you know? You have to check the definition given in theorem 1, which is you have to check the addition and also the scalar multiplication, okay? So here it's given that V is a subspace, and then you have another subspace given by this W. This W is also a subspace, okay? So theorem 2 here says that if V and W are both subspace of a vector space U, then the intersection of V and W, denoted by this, is also a subspace of U. Okay, so you have this vector space U, this box here, and then you have two subspaces here. So the middle part is the intersection. V intersect with W. So this one here is also known as subspace based on theorem 2. Alright? Provided that you have shown that V is a subspace and W is also a subspace. Then only you can conclude that the middle part here, which is V intersection with W, is also a subspace. Okay, so let's see. There are two exercises here. So let's see the first one. Which of these two subsets is a subspace of R2? Okay, so let me just sketch it. This is page 3. This is going to be page 4. Okay, so subspace. This is example 5, part A. Okay, to check subspace of R2. Okay, part A. So you are given x plus 2y equals to 0. Alright. So this is interesting. All this while, if you notice, we have only been checking the plus and the scalar multiplication. Okay? But then how many properties are you supposed to check? Initially, you have to check 10 properties. Okay? So these are the only, in all the examples, I've noticed that we only check these two. Okay, one more interesting fact that I want to add here now in this example is, let's go back to the slide at the front here. Let me see which slide it is. Okay, this one here, slide number 23. All right, refer slide 23. Okay, so if you see in this slide here, page 23, you can see there is a 0 element, property number 4. Let me just write down here. Property number 4. Property number 4 is actually emphasizing on the 0 vector. You see, for a set to be a vector space or a subspace, you have to check the addition, the scalar multiplication, and also you have to check the 0 vector and so on. So basically there are 10 properties that you need to check. Okay, so all this while we have been just concentrating on addition and also scalar multiplication. So now I'm going to show you this example here, which is actually playing around the 0 vector. All right, so let's go back to the example. Okay, so you have x plus 2y equals to 0. Okay, so in order for a subset to be a subspace, you need the zero vector of the vector space. Okay, so I'm just going to write it down here. So in order for a subset to be a subspace, you need 0 vector. I'm going to denote as 0 like this of the vector space. To be included. Okay. So now let's check if I want to check if the 0 vector is included inside this or not. Okay. Oh, sorry, I think I wrongly wrote part A. Okay, no. Okay, this one is good. So you have x plus 2y equals to 0. Okay. So how am I supposed to check if the 0 vector is included or not? So what I'm going to do is 0 vector here, because we are working in R2. So 0 vector here is going to be denoted as 0, 0, which is actually the coordinate of x and y. Alright, so I'm going to take this x0 and y0. I'm going to sub into this line here. So I'm going to have 0 plus 2 times 0 equals to 0. Okay, in other words, 0 plus 0 equals to 0. 0 plus 0 is 0 equals to 0. So left hand side is equals to the right hand side. No problem in that. Okay, so for that reason, 0 vector is included. 0 vector is included. Okay, so you can make a conclusion and say that so conclusion here is that part A is a subspace of R2, right? And how about part B? So in part B, you are given this equation here. You have x plus 2y equals to 1. So you have x plus 2y equals to 1. So back to the same definition here. In order for a subset, which is this is a subset here, to be a subspace, you need 0 vector of the space of the vector space to be included. Okay, so again, this is in R2. R2 implies that you have two coordinates. Let's say two coordinates of 0 vector is given by 0, 0. Okay, this is actually coordinate x and also y. Okay, so I'm going to take this x0, y0 and sub into this subset here. So I'm going to have 0 plus 2 times 0 equals to 1. 0 plus 0 equals to 1. This is 0 equals to 1. So you tell me now, is 0 equals to 1? No, it is not. Right? So you can see that the 0 vector is not included on the subset of x plus 2y equals to 1. So for that reason, you can conclude that B is not a subspace of R2. So you see, there are multiple ways of showing if a particular subset given to you is a subspace or not. So basically, what are the different ways that we have gone through so far? We have checked the addition. We have played around with the scalar multiplication. And then now, I have shown you also the concept of checking the 0 vector, if it's included inside the subspace given to you or not, okay? Alright, so, okay, let's see one example here. One complete example. So this is page 3 and 4. I'm going to scan all this and upload on Goals for your reference. Let me grab a new paper. Okay, so this example is actually not inside the lecture note. I'm just going to write it down here. So determine if the following subsets are subspaces of R3. All right. Okay, so let me just open the. Okay, so the first one, part A. So let's say you have. First one is given by A, B, 1. Okay, so you want to check if this is a subset. Okay, it's a subset. You want to check if it's a subspace of R3 or not. All right. So let's first of all check. So there are basically three things that I want to check: addition, scalar multiplication, and also the 0 vector. Okay, so let's check the 0 vector. If it's gonna, so what is the 0 vector here? Can a 0 vector be inside here? Because 0 vector in R3 is given by what? It's given by 0, 0, 0. Am I right? Okay, so as you can see, if you compare this to this one here, there is no way you can get a 0, 0, 0 out of this. Because A can be a 0, yes, no problem in that. B can also be a 0, no problem. But the problem actually lies here at the third coordinate. This third coordinate is already given a fixed number 1. But in 0 vector, the third coordinate is supposed to be a 0. So from there, you can see that this part fails. Alright? And then how about the closure under addition? So closure under addition, for example, for this part here, I want to extract two examples of vector from here. Let's say, for example, I want to take 2, 1, 1 plus with, what's the other example that you can take from here? Any example can be 3, 2, 1. Okay, the first coordinate can be any number A, second coordinate can be any number represented by B, but the third coordinate have to be fixed 1. Okay, let's add these two vectors here. You will get 2 plus 3 is 5. Okay, 1 plus 2 is 3, and 1 plus 1 is 2. Okay, so you tell me now, is 5, 3, 2 of the same form of this? I don't think so, because 5 and A, there's no problem in that. 3 and B, no problem in that, can be any number. The problem lies at the third coordinate again. Okay, the third coordinate here have to be 1. Unfortunately, when we add these two, we get a 2 here. So this property fails as well. Let's try scalar multiplication, okay? Let's say I'm going to take any scalar, 2, for example, and I'm going to take any vector in this form here. Let's say I'm going to take 2, 3, 1. Remember, the third coordinate have to be 1. The first two coordinates, you are free to choose any number that you want, okay? So if you scalar multiply this, you're going to get what? 4, 6, and 2. Okay, so you tell me now, is 4, 6, 2 of the same form as AB1? No, it is not. The problem again lies at the third coordinate, because this is supposed to be 1. But then when you do scalar multiplication, you get a 2 here. So this one is also not satisfied. Okay, so you can see in this example here, all three properties are not satisfied. So conclusion is AB1 is not a subspace of R3. Okay, so let's have a look at one more example. For, let's say, for example, A0C. Okay, let's say I have A0C. So again, A and C, you are free to choose any number that you want, but the middle coordinate, the second coordinate have to be a 0. Okay, same thing, I'm going to check three things here, plus scalar multiplication and also the 0 vector. Okay, so let's check the easy one first. 0 vector. Can you get a 0 vector from here? 0 vector here means that you need a 0, 0, 0. Can you get a 0, 0, 0 from here? Yes, you can, because you can set A to be equals to 0 and also C to be equals to 0. So from there, you're gonna get a 0, 0, 0 vector out of this. So no problem in this. Let's try vector addition. Let's say I'm going to take 2, 0, 3 plus with, let's say, any number 4, 0, 5. Okay, remember the first and the third coordinate, you are free to choose any number you want, but the middle coordinate have to be a 0. So let's add these two vectors here. You're going to get 4 plus 2 is 6, 0, and 8. Okay, so you tell me now, is 6, 0, 8 acceptable to be in this form? Yes, it is, because you are free to choose the first and the third coordinate, but the middle one have to be a 0, so no problem in this one here. And now let's try scalar multiplication. 2 multiply with, let's say, 2, 0, 3. What are you going to get? You're going to get 4, 0, and then you're going to get a 6. So you tell me now, is it acceptable? Yes, it is, because it is of the same form here for any number A, 0, 0, 6, any number C. Okay? So you can make a conclusion and say that A0C is a subspace of R3. Good. Okay, so I hope these examples help you in understanding what is the meaning of subspaces. Okay. Alright, so I'm going to continue all this in another 1 hour lecture recording. I'm going to stop this one first and try to upload this on YouTube. Okay, thank you.